I'm going to start. So, welcome everyone. Welcome to Madrid. To everybody, it's not from Spain. I hope you're having a great time here. So, I want to make concurrency groovy again, but groovy in the sense of cool, you know, not in the sense of using groovy precisely. Well, first I'm going to introduce myself. I'm Alonso Torres. I work in Kaleidos. We are a Madrid-based company. Sorry? Better? Okay, so yeah, I'm a Groovy developer. Mostly we do web applications. Also, I'm a functional fan. I like. I usually program in different languages, just like Scala. I hope the Groovissimo doesn't kill me today. Foremost, it's important I'm not a Trump supporter, even if the title may indicate otherwise. As I was saying, I work in Kaleidos. We are like a very big, happy family. We are a small company. We're only 20 people. But we are not only Groovy developers. We have Python developers. We have JavaScript developers, sorry. Some people like Clojure. That joke gonna cost me on Monday. Okay, so there are Clojure fans. We have also Scala fans and Go fans. Yoo-hoo. And that's when things get messy. When you start discussing everybody's favorite language, things get messy because every language has its own concurrency features, no? For example, actors in Scala, very famous. The Clojure data structures, Go channels. Even Python, they don't have threads, but they have GPU parallelism. The event loop, I mean, one language that only has one thread, they are famous for concurrency. It's amazing. But what about Groovy? As I was saying, I'm a Groovy developer, so what's cool about Groovy? Well, yes, we conk. Okay, he's Guillaume Laforte. He's the team leader of Groovy. Groovy has many features. Some of them are very cool for concurrency. Indeed, we have, well, JVM. It works under the JVM, so it has, out of the box, a lot of features from Java. Also, we have static and dynamic typing. Again, very cool. If you want, you can change from one type of programming to another. It offers different advantages and disadvantages. Also, and most important, we have metaprogramming and DSLs. This is one of the key features because we can offer very cool abstractions over concurrency. And one very big feature is GPars, of course. If you install GPars with SDKman, you have it out of the box. If you use Groovy as a dependency, it's just one line in your build, and you have all the powerful features that GPars offers. Okay, that's very nice. Maybe you knew all these things. But there is also a thing we must remember, that concurrency is hard. And tests are even harder. So the shit hits the fan in a big way. And we have a Spock. It's true that Java can use Spock, but Groovy is the natural language to use Spock. In fact, you have to do the test in Groovy. Okay, so I want to talk about 4 topics. The first is what are we trying to solve? What are the problems? How are the building blocks? We are going to steal. And finally, I want to talk about testing. Okay, design. So I was saying concurrency is hard. But what's a real problem? Because concurrency normally is not our problem. Our problem could be performance. So we want more speed. And we usually use parallelism. What's parallelism? Is if you, instead of having only one task at one time, you have several tasks working at the same time. Pretty straightforward. The other problem we want to solve is feedback. I mean, are you still alive? For example, if we have a web server, we don't want to wait for every process, every request to be processed before I have mine. Or if we are using well, we use asynchronous processes for this. If I have a graphic interface, some stuff is happening in the background, I want real-time updates of how is my progress. And the last problem I think there is for a use case for concurrency is if we need more resources, we need more RAM, for example. Usually our problem is bigger than the resources available, so we use a technique of distributing the processing. So instead of using one machine, we usually use several and one master to control them. Okay, so we have our 3 problems we want to solve, and we have 3 solutions. Okay, but now there is a new problem. We have non-determinism. What it means is that the different pieces execute at the same time. So we can be sure of which piece is going to execute before the other. We don't know the order. We also have the problem of correctness, because it's very easy to think about a sequential problem, but when you split it in several parts, it's now a new problem. You have to be sure it's correct every time. Also coordination. These moving pieces maybe depends on each other. Maybe you have to execute one before the other. Performance. It's funny because one very common thing is that the performance of a parallel solution is worse than the original one. Access. Maybe some of the processes need a specific access to one resource, or maybe the other way around. Maybe we don't want every process to access one variable. For example, communication. Yeah, we have to send the data to these processes from the main thread. Sorry, I don't want to say thread yet. System resources. Some of the processes to be executed is expensive. It's not free. Okay, so this is what you hope for, and this is what you get. It's a mess. So you had 3 problems, and now you have 8. Cool. There is this famous quote. If you are using regular expressions, you have 2 problems now. Okay, with concurrency, we have 8 problems. At the same time, they are executed concurrently. Okay, so let's see how we can solve this. I'm going to talk about these 5 techniques. Maybe you know some, maybe others don't. I hope I can show you some new cool things, even if you are an expert. But I'm not really an expert. I mean, I think I know some stuff. I want to make an introductory talk, so I'm not going to go very deep into each topic. It's more an overview of the different mechanisms we have. Okay, so I hope you enjoy it. But we need a problem, okay? For each one of the techniques, I want to solve this problem, factorial. I suppose you are familiar with what's factorial. I choose this problem because of 2 reasons. First, it grows very quickly. It's very easy to try it for very small numbers. As you can see, for 5, 10, it's very small. But each 0 you add to the input, it grows very fast. In fact, 1,000 factorial barely enters the slide. So that's one reason. The other reason is that this is the product, multiplication. And it has very cool features, the product. The first is a binary operation. It's the same type for input as output. The second reason is that it's commutative. We don't care about the order, and this is very useful, as I was saying before, for the determinism, because we don't really know which process is going to be executed first. So we could use this property. Associative. We can group them. If we can group them, we can execute it in separate. Even if you, well, the other day in Kaleidos, I was showing the talk, and a colleague of mine said that, oh, in this kind of talks, you always, people always use mathematical things to show it off. Why don't we use real problems? I mean, okay, yes, but it's easier for a 50-minute talk to use something everyone is familiar about, not to use a new problem that you have to explain. But I hope you can be aware of these properties if you are using a real problem. If your problem doesn't care about order, if your problem can be grouped in big things that can be combined later, that's a very good candidate for parallelism and for concurrency. Okay, this is the serial solution. I have to start somewhere. I know I could use more fancy stuff like inject or maybe streams, but yeah, I want to let it simple. By the way, I don't know if you knew, I didn't know before the talk, I discovered it preparing the talk, is that in Groovy you could use small g for literals big integer. That's very cool. Because as you have seen before, the 1000 factorial is more than an integer. Okay, what's the time? How long does it take to run this factorial? It's almost 7 minutes for 1 million. Okay, so we have a performance problem. So let's parallelize the solution to see if we can improve over this. Okay, as I was saying, I'm going to use these methods. You can check the code of all the methods here. Yeah, you can. I will put again the URL at the end of the talk. But if you don't want to listen to me, you can just check the code, if that's what you fancy. I'm going to wait a couple of seconds so everyone that wants could grab the... Okay, so first threads. What are the threads? Okay, so threads are the basic unit of concurrency in the JVM. They are managed by the operating system, so you don't really can tell native threads. You really can't tell when it's going to be scheduled. The operating system has its own ways of handling these threads. There is always at least one thread. It's the main thread, no? The thread where the main code is executed. This is a first approach to thread programming. You create a thread very easily, thread.start. I don't know if you are Java developers, but this is already very cool. Very few lines of code for the same task in Java is much longer. We store the threads. The arrow operator, what does is stores one thread in the array I had up. And using the spread operator, we can wait until every thread is finished. What is happening? We have one thread, it's the main thread, that spawns a lot of threads, one per number. And everyone answers to the main thread. Okay, let's see how this problem solves coordination and communication. First, we are sharing memory. We are communicating with the threads, sending our local variables. And the thread's access to main memory, to the shared memory. And finally, we coordinate with every thread by waiting. Pretty straightforward. Okay, but what happens when we execute this code? Factorial of 10, the expected result. Again. What happens? I continue, what's happening? Again, a different result. You can see it's non-deterministic. It's not correct. And why is this? Because of the visibility. Maybe two threads run at the same time on the same variable and they collide. We have to synchronize. What this means, that this block have to be safe. It's the infamous mutex, mutual exclusion. We have to lock. So now only one thread can execute this line at the same time. Okay? Now at least works. But the time is worse. And it fails. Okay, we are doing a great job here. Okay, before addressing the error, I want to solve the access to the same variable. Java, out of the box, the GRL array, has a lot of features in the java.util.concurrency. And we can use atomic variables. What are atomic variables? They are variables that have atomic access. Instead of using a explicit locking, we try to do an operation, and if we can't, we try again. You can see the code is almost the same. The only thing that has changed is that instead of having an integer, a big integer, I have an atomic reference. But if you know the API, you should see something strange. That just I'm multiplying this with an integer, and you should be suspicious because I'm using a bit of magic. This is another very cool feature of Groovy. It's a bit of magic, but come on. We are using Groovy for something. So what I'm doing here is I'm adding the multiplication operation to an atomic reference. This is the API for atomic reference. You basically repeat the same operation until you succeed. So the API of compare and set is if I have read the old value, I can try and put the new value. So it's a while loop. You retry until you succeed. Okay, now we are safely writing to an atomic variable. Okay, now back to the error. Yeah, the problem here is that we are creating thousands of threads. So the solution is not creating thousands of threads. We use an abstraction called the thread pool. So now instead of being us, the ones that do the new thread, we delegate this creation to a thread pool that basically reuse the threads. Instead of calling new thread, we do submit, and the same code. Instead of here, the coordination is different. We use get instead of join, but the usage is the same. It will block until the result is given back to us. Now, this is the time. Well, at least it doesn't crash. But the times are not very good. It's even worse than the serial solution. Not good. OK, so what's the problem here? And this is one of the main things I want to tell you is sometimes we start doing parallel stuff. We try to parallelize everything. But that's not the correct approach. The good thing would be to find a middle point where the bigger stuff is doing in parallel while we have a small enough chunk to do it in serial. So instead of having one thread per task, we have threads that do a lot of tasks. Maybe we have a lot of threads, but they are doing more stuff. Yeah, I will going to use a serial product for my next slide. Basically, it receives from and to and multiply every number from to. Okay, so we divide the problem in batches. We divide batches, slices, chunks, whatever you want to call it. And then instead of having one number per thread, now we have a thread per batch. And product, it's serial. It's not parallel. Okay? We have done this. And this is the result. As you can see, we're improving a lot. And I mean a lot. So, yeah, the first thing I want to show you is that not everything has to be parallel. Okay, but we are still having the shared state. And that may cause a lot of trouble. As I was saying, threads are competing against each other. Also, we are looking for everyone to access one part of the code. That's not good, because we have a bottleneck there. And also, we have a lot of problems with non-deterministic, not determinism. But okay, memory-wise is good because we only have one memory position, so everything is not bad. But there is another way. Functional style programming. Sorry, I have to talk about this. Don't be scared about functional. Okay, instead of having several tasks that are running against data, we reverse the order. We pass functions to data, and we only describe what we need to be done. And the methods on the data will manage the parallelization. Of course, this only works if the data you pass is immutable, because otherwise, if the function you pass have side effects, they can do the optimization of parallelization, for example, because the threads or the mechanism doesn't know if it's going to be a side effect that breaks the correctness, for example. Again, Java has some cool things that we can use because we are using Groovy and we can use it better. Streams, great example. This is functional programming in pure form because you really are creating a stream from a range. Then you ask that do it in parallel and just call your product function. And that's it. Very easy. Okay, you have to get used to it. That's a problem. Not everybody can, it's good at thinking about functional style programming. And also, for certain problems, it's easier than others. It's harder to distribute. Yeah, a higher level of abstraction means less flexibility. Before, I've shown you several techniques for threads. Some were incorrect, but I have a lot of options. To do the factorial in functional style programming, I don't have that many options. But the times are very good. You can see that I've improved already. I hope you are following me. I hope. Okay, I'm going to talk about GPars now, because GPars is so cool for concurrency. We have it very close at hand. It's very groovy in the sense of it uses the features that provides like DSLs, shorthands, the improvements over collections. So GPars has a lot of features. I'm not going to talk about every one of them, but some of them. But yeah, GPars all the things. Okay, the first thing I want to show you is parallel collections. This is the same example as before, without slices or batches. Yeah, we have removed the thread pool. We only need with pool and a closure inside that tells what to do. And GPars adds a new method called each parallel, that instead of going one by one, it does the each, but in parallel. Okay, the problem here is that we are still using the same old approach. We are sharing a state, we are using the atomic reference. So really what I have removed here, it's the threads and the thread pool. Well, that's an advantage, but we can do better. Well, the time, so you have the reference. It's better than the thread with the pool, but it's still worse than the batch. Okay, fork join. This is something not very much people know about, but I think it's very cool. Basically, fork join uses a divide and conquer approach. If you have a task that can be split in half, it's perfect for this kind of, well, split in half on more chunks. It's perfect for this kind of approach. It's also a concept inside the Java, in the JDK. They have the fork join thread pool and the fork join task. So really, it's the GPars is providing is a wrapper, a Groovy wrapper over this stuff in the JDK. And we are not sharing a state. We are using functionalist approach. As I was saying, it's divide and conquer again. Okay, what is this about? We have our factorial. We are trying to multiply from 1 to 100. So we split in half. We do one half of the numbers in one side and the other half. And then again, we split again. We multiply the numbers, and we have our result. This is the overview, okay? I'm going to show you now the code. This is kind of like a recursive function. Run, fork join, and fork of child, they are part of the API. So it's not something I've implemented. This is out of the box with GPars. You only tell that's like a method declaration there. And this is our base case for the recursion. No? If the difference, if we have a chunk of 1,000 numbers, do it in serial. And now, fork of child, we delegate there to do its magic, no, in parallel. These are the methods that are part of the, well, get children results is also part of the API. This is the result. You can see an improvement there. It's very fast. Okay, so fork join. It's very fast, as I was saying. It runs over Java's API, so potentially you can do this in Java, but believe me, it's much harder. Of course, it's not suited for every problem. We need a more flexible approach, but that has the same advantages. And here is where actors come in. And I don't mean this. Actors, they are processes, asynchronous process. They usually encapsulate internal states, so they own an state. And we send to actors messages to work with that state. Another cool thing about actors is that the abstraction works very well for distributed systems. So, for example, you don't care if an actor is in my machine or in a remote machine, because the message should be immutable. You have to be able to serialize it. So the same abstraction works for parallel programming and distributing programming. So this is what it looks like. We have our main thread, our main actor, sorry. This actor will call to these other two actors, sending messages. And these two actors will do the same. We are really doing the same as the fork join. We are sending half the numbers up, half the numbers down, and recursively, the other actors will send their half to those other actors. When they are finished, they answer, and finally, the main actor will be in charge of creating the result. So, of course, there are two types of actors here in this solution I made. The first one is the coordinator. He's the one that starts the chain, and the ones that finally answers to the API. Okay, so we have a state owned by the actor. We start a calculator and wait for the answer. Join needs to synchronize with the main thread. Okay, span calculator. This is the actor that does the real job. Receives the message that comes from the coordinator. When it's small enough, does it in serial. Again, this is very important because it's key to improve the performance. Because if you do smaller chunks, you spend more time creating the actor and sending the message than doing the operation. And okay, this code is the next slide. Basically, again, if we are not in the base case, we split in half, create two new calculators, and wait for the messages. Very simple. And this is the time. As you can see, we have improved even more than with ForkGen approach. Okay, that's the building blocks I want to talk about. But now let's steal. Yeah. So join me to the dark side of Groovy. Okay, closure. I hope the Groovissimo is not here. Okay, what I want to talk about is how we could use features from other languages in Groovy. And the first one I'm going to steal is from Clojure. Clojure is, I don't know if any of you don't know Clojure, but it's a functional language for the JVM. It's very famous for its concurrency, specifically for the data structures, but there are other features, very cool features. Yeah, but at the end of the day, it's bytecode, so maybe we could use something in our code. This is the same. I used the simpler approach, so you could see the difference easier. But yeah, of course, here I'm using GPars, but I'm not doing the batch thing, so this could be improved. Yeah, the API. We are creating an atom. Basically, the atom is kind of an atomic reference. It holds the state inside. But instead of accessing directly to the atom, we are calling swap. Swap is a function that receives a function. It's functional programming. We call swap, and we send the operation we want to do with the value. Here, we want to multiply the old value that was stored inside the atom with our new value. Same thing, okay. So we finally coerce this. This is IFN. It's an interface given by Clojure, and it's and we have to coerce. Otherwise, will not work. Will not coerce the closure to an IFN. Okay. Wait. Sorry. Okay. Well, the time is not important. As I was saying, I could improve over the time with the other techniques I've talked about. Really, I've put the time more for reference because I've done that for every other. Akka. I don't know if any of you are familiar with Akka, but it's very popular in the Scala space. Basically, it's a concurrency toolkit for Scala. It's used mostly for actors. Yeah, it has very cool features like distribution on actors and remoting. And also has Java bindings. Yeah. And you could use it from Groovy, of course. This example is much harder than the other one. The Akka API It's not very straightforward from Java. Of course, from Scala is another matter. But yeah, you could do it. You can see here I'm doing the same as I was doing in GPars. I'm spawning a calculator with the whole number, and then I wait for the answer of the calculator. This is what the main body of the calculator looks like. You have to make a match for each one of the messages it could receive. Here, the same message. I have two cases before because I want to do different things depending on if a message with the first number has arrived. Yeah, the same thing. We have the base case where we only reply with the serial product. Stops the execution. This is important because otherwise it will hang forever. The actor will not do anything. And yeah, I'm creating two actors and send half to each one. I know it's hard to follow this code, but you have, I will repeat the URL for the source code if you want to check it out. What about the time? Well, it's very bad. I don't know why, as I was saying, I'm not an expert, and in Akka, I'm not an expert at all, but for me, it's very clear that GPars actors are far, even if I made some mistake in the configuration, the times are very different. So you will be thinking, what's the point then on using Akka? Well, first, there's a very big community. And second, it has more features than GPars. Better error handling, more abstractions for routing schedules, persistence. You can save the state of an actor in disk, for example. And the fault tolerance, it's also better. And you could distribute actors. Okay, talking about distribution. Spark, another thing we are going to steal. And this is very cool. Yeah, basically Spark is distributed functional style programming for Java and Scala. Again, we can use the bindings that give to Java to use it from Groovy. Okay, RDDs are the concept of Spark for streams. Okay, you can think, it's easier if you think that way. RDDs are the streams of Spark. This is how you start a Spark environment. Here I'm telling that I'm not going to use the distributed solution. I'm going to use local. So that means that using my local machine spawn 8 threads. Yeah, it's very similar to the streams approach. It's only we parallelize the whole set of numbers, creating a new RDD, and then just reduce to multiply. We have to call the hydrate because otherwise closures are not serializable by default. Because closures at the name closure comes from the fact that they are closing over the local scope variables. So you need to remove those variables before sending it to a remote location. And as you can see here in Spark, the time is much better. It's very cool, Spark. Okay, we have stolen, so now we can pass to testing. Okay, this is, I want to basically show you 3 cool things about the Spark for testing concurrent asynchronous applications. The problem with testing asynchronous code, for example, this code, I create a new uploader service, and I start the uploading. The closure I send here is the progress update, so I will receive progress for the typical uploading process. And this is my first try. I try to start the process, and then I hope when you after you call start, the process has finished. The problem is that when we call is done, it's not yet done. It will take time. But the start returns immediately because it's asynchronous. So there's Spock has blocking variables. Yeah, maybe it's a bit small. But okay, so what I'm doing here is overriding the set is done method, and I'm when the uploader service writes to that variable, it will set a blocking variable. At the end, is done.get will stop until it's done. Second, async conditions. Very quick. Normally, if you have a start method that invokes a closure asynchronously, you can't make a search there. But with evaluate, you could. It's just creating a async condition, then call evaluate, and at the end, await. So the test doesn't finish until the condition is called. There is, of course, a timeout and a default timeout. If you can change it. And polling conditions. And this is even better. What this does is eventually repeatedly will poll for a condition, will wait until this condition is achieved, or a timeout is, or there is a timeout. If it takes too long, it fails. Okay, so that's it. This is the mandatory kitten photograph for a presentation. Yeah, just as a recap, I've shown you that, I hope I've shown you that Groovy is very cool for concurrent programming. I hope you know a bit better what are the problems that we face with this kind of model. These are some of the things I've tried to show you. There is a lot of more stuff. GPars has lots of abstraction, but 45 minutes is not enough for talking about all that stuff. We have data flow, CSPs, transactional shared memory. There are a lot of things. And of course, we have to keep an eye on other languages so we can steal from there and use it from Groovy. And remember Spoke. We have hope. Yeah, Groovy is plain awesome. Thank you.
Any questions?
We have time for questions. Yeah,
So, what have you learned yourself while preparing this demo?
yeah. Good question. Yeah, I've learned a lot. For example, the big literal thing I didn't know. Fork join, I've read about fork join, but I didn't know it was that fast. So I knew the concept, but I thought it was a very nice link with fork join and actor. So that's why I tried to research more about that. And then I was very surprised when I discovered that it was so fast. What I discovered also that Akka is much slower than GPars. I don't know if that's my fault or is Akka's fault. Maybe both. Yeah, a Spark, I've done a Spark from Scala, but really it's the first time I did it from Groovy, and I thought that was very cool. Yeah, a lot of things, really. I've learned a lot. You're welcome. Any more questions? Okay. Well, that's it. Thank you very much.